Welcome back to che531. In this video, I'll be talking about the first approach to find a zero of a function. And the method is called bisection, which means we're going to start with two guess values, and every time in the iteration, we're going to bisect the distance between A and B. So we talked about the theory part of it in the last video. In this video, I'm going to show you how to basically write a script in Matlab. Okay, so the script is very short. Let's say I want to find the root of z tan z minus 1. Okay, before we begin, we need two guess values, and to do that, the best way is to plot the function and find the guess value. So I'm going to plot the function, and to plot the function, we're going to create a vector z from, let's say, z equals 0 to maybe 1000 to, let's say, 10 pi over 2 minus 0.1. So this is basically 10 pi over 2. Assume that I'm going to look at the interval from 0 to 10 pi over 2, which is 5 pi, and use 1000 points in between to plot the function. Okay, so I define my z as a linear space, which means create a vector from 0 to 5 pi, which is 10 pi times pi over 2, or 10 times pi over 2. Slightly smaller than that, actually, minus 0.1. But anyways, you can think of this as like 10 times pi over 2. And you divide it to 1000 points, including the two ends. So you get a vector that goes to z, and then you do the z tan z. By the way, because this is z, we do element-wise multiplication. Okay, so you get f of z, and now we're going to plot. So we're going to plot f of z as a function of z with solid line, color blue, line width is equal to 2, and we're going to hold on to that figure. So put the breakpoints and run it so we can see what we get so far. So the function actually peaks at some point. So this is like, okay, this is z at about 2, less than 2, which is pi over 2, right? So we know that tan at pi over 2 goes to infinity. So this is pi over 2, this is 3 pi over 2, this is 5 pi over 2, this is 7 pi over 2, and so forth. So the function is periodic, and so this is what I get from 0 to 10 times pi over 2. Okay, so this is basically the result of that line. Then we're going to also draw a line with solid black, line width of 1, from 0 to 10. So if I run this one more step, you're going to see what that line is. So there's a black line going through this. You can see it. It's very tiny. It's right here. This is a black line that just plots. So it goes from 0 all the way back. 0 is right here. It goes from 0 to 10 right across the x-axis. So with x between 0 and 10 and y between 0 and 0, which means y 0. So you get basically the x-axis. So just plotted x-axis because there was no x-axis here. It was kind of hard to see, you know, where the x-axis is. So basically I replotted x-axis. Next I'm going to plot the lower bound and left bound and right bound, because this is periodic. I have to basically find an interval and focus on that to find a root, because this function has many roots. The question is which region of this graph I'm going to look at to find a root. So put the left boundary at 0.1, right boundary is 4. So 0.1 is somewhere here, 4 is somewhere here. So basically I'm looking at this area. So I'm going to plot two dots, one at lower bound and y equals 0. The other one is at left bound and 0, and right bound and 0. So here it is. So we have 2 points with the size of 40. Okay, and I'm going to focus between these two to find the root. So I'm going to limit my x from 0 to 6. So here it is, from 0 to 6, I limited my x. I'm going to put x label, y label, and I'm going to set all the font size to 18. So let's go 3 lines down, and there you go. So font size is 18, x label, y label. It's much clearer now. Okay, where is the root? So the root is, if I focus between these 2 points, the function starts from here, goes up, and then starts from minus infinity and then go up there. So I would guess the root is somewhere, around this area. In this area, it's always above 0. In here is below 0, but then here is above 0. So between less than 0 and bigger than 0, it has to hit 0 somewhere. Okay, so now I have my guess values, A and B. Okay, so my A is going to be somewhere close to left bound, and my B is going to be the right bound. Okay, so we're going to define a function. X tan x minus 1 is the same function we want to find the root of, but I put all of them in like one line. This is like inline definition of function. My guess value is going to be left bound, right bound. My threshold is 10 to the minus 4, and I'm going to iterate up to 1,000, up to 100 iterations. If I cannot find it, then I'm going to quit. So how do we define this function func? It's down here. Let me see. Yeah, this is func. It gets the function definition, which we define it right here. So this goes to the function definition. Lower bound goes to A, right bound goes to B, or sorry, left bound goes to A, right bound goes to B. 10 minus 4 goes to epsilon, and maximum number of iteration goes, or 100 goes to maximum number of iterations. Okay. So we're going to do some printing. First, we're going to print some like headers. Number of iterations, A, B, P, and FP. So if I stop the code up to here, so you can see the results so far. So I get 4 headers, or 5 headers, for iteration A, B, and P, which is the average of the A and B, and F evaluated at point P. Then every time I go over this cycle, I check if FA times FP is bigger than 0. Then we would say, hey, this is the wrong guess value because FA times FP should be less than 0 to basically sandwich the root. If FA times FP is not less than 0, that means the root is not between A and B. So we're going to display this error or the warning. Otherwise, we're going to find a P. We're going to find the error, which is the F evaluated at point P. We get the absolute value of it because we don't care about the sign of the error. We just look at the error itself. And then we're going to do this in a while loop. As long as error is bigger than epsilon, the threshold we defined before, then we have to iterate. So we iterate, we check FA times FP this time. If less than 0, then we're going to replace B by P. Otherwise, we're going to replace A by P. After that, we're going to find the median or the average of AB. We're going to call it P, calculate F of P again, and recycle. So there are a couple of print commands in between. In Matlab, the print command is fprint. So we're going to fprint the number of steps A and B and P, an absolute value of FP, which is basically the error. So we're going to print them using this format. So this means a float number with 4 digits total and 0 decimal digits. This means basically we're going to print A in scientific form with 4 decimal digits, total 11 digits, and we're going to basically show the power of 10 as E. So this is basically scientific form. Like 10 to the power of 5, we can write it 1E5, and that's pretty much like this. So we're going to do a scientific form for the other 4 numbers, A, B, P, and the error. Okay. In case if we hit the maximum number of iterations before finding the root, we're going to have this error statement that maximum number of iterations has reached, and we're going to quit the execution because we don't want to run this forever. Otherwise, you're going to kill your laptop. So let me run the code, and there you go. It stopped after 13 iterations, and you see that I start with A and B called 2 and 4, 2 dots that I put here initially. So this is my A, this is my B, and then the root has to be between the 2, and this is the root that was found at the end. Okay, so you see that at the end, A and B becomes actually identical, so they're almost the same, no difference because they get closer and closer and closer. And B is always average of A and B. So you get A and B, you get the average, you get P. And at the end, because P is between A and B, if A and B are the same, then P has to be equal to A and B. and you see that the error, which is f of p, goes down. So start from this 1, basically, and the error goes down to 10 minus 6. This is less than the threshold we put. The threshold I put there was 10 minus 4. So the last iteration is bigger than 10 minus 4, and the next to the last is bigger than 10 minus 4, and the last one is less than 10 minus 4, so I'm going to stop. So then the solution would be these three. They are identical, so any of them would be the solution. The solution is 3.4254, and if you plug that into the original function of z tan z minus 1, you have to get 0. Okay? All right, so that was bisection. The next method we're going to talk about is Newton's method, right? So in Newton's method, well, the drawback of the bisection is, first of all, it works only for one dimension. If you go to two-dimensional problem, like you have x and y, you want to find the root of a function which is function of x and y, you cannot use bisection. Second, the convergence is rather slow. That means even for this simple function, we have to go through 13 iterations. And so if the function becomes more complex, then we may need to go to, even more than that, like maybe 1,000 iterations. So the convergence, we can say, is small or slow. Okay. So in Newton's method, you're going to basically avoid these shortcomings, first by making it faster to converge, and second, make it such that we can use it for multi-dimensional cases. So in Newton's method, the way is we start from one guess, okay? And so let's say my guess is supposed to be here. And let's say this is the function, and my function hits the x-axis right here. I start from this point, and my goal is basically to get that point. So at this point, we draw a tangent. So this is a tangent line to that point. And from a tangent line, we can get the slope. So the slope is nothing but the derivative of the function at this point, because by definition, derivative means a slope. Okay, so if I have the slope of this line, and I have this point, so I know the height of that point, which is where the function evaluated the guess value. So I have this height, I have this slope from this triangle, I can calculate this base. So this base is nothing but f of x at point xn divided by the slope, which is the derivative at xn. So f of x divided by f prime of xn. So this gives me the base. I subtract this base from the original point, which is xn, so xn minus this base, it gives me the next iteration, which is xn plus 1. Then I iterate. So that's basically the gist of Newton's method. We start with a guess, we find f divided by f prime, subtract it from xn, we get the next x, and we put it back in here and cycle through this. So here's the pseudocode. We start with a guess value, we find the derivative, we find the function at point x, we calculate this, subtract it from the original guess, we get the new guess. We check if the function at that new guess value is less than the threshold, we're going to stop, which means convergence. If this is not less than the tolerance, we're going to cycle through this, which means we haven't converged yet. All right, so let's look at the pseudocode for this. And so the pseudocode is, so let's say Newton's method is going to be this one. I'll open it. Okay, so we're going to clear the screen. We're going to clear all the variables. We're going to close all the figures. Well, I have a couple of examples here. I'm looking at example 6, but that doesn't matter. Let's look at example 1. So I'm going to just uncomment this, and here's example 1. Okay, so in example 1, we're going to look at z to the 4th power minus exponential of z plus 1. We're going to find the root of this using Newton's method. So stay tuned for the next video on how to solve this same problem using Newton's method.